Welcome again to another edition of the Osteopathic Lyceum podcast. What I'm going to attempt to do today is speak about something that I saw probably about a month and a half ago, and also essentially relate this as, say, a more recent topic to some of the challenges with osteopathic diagnosis and osteopathic claims. Okay, so what I'm going to do is share my screen, and I'll obviously be reading from it. What we're actually talking about, or what we're going to use as an example to bring forth some concepts, is this thing that I came across that was talking about how artificial intelligence is going to be able to read your thoughts. It's going to know what you're seeing. It's going to be able to predict what you're going to do. Now, while that sounds like a big claim and it sounds very interesting, it's actually doing what would seem fairly well as far as the claims this research would make of itself, but it's definitely not making good on the promises that articles, say popular articles or news articles speaking about it, make it seem like. So what we're going to look at here, and we're going to go through the introduction, and then I'll point at some different things in this paper, is a paper called Decoding Visual fMRI Stimuli from Human Brain Based on Graph Convolutional Neural Network. And this is from 2022, I believe. So we're not going to go through we're not going to go through the abstract as such. I'm going to read from the introduction, and then I'll go down to a much deeper portion of the article to talk about the accuracy that they're achieving, which is actually, for what they're doing, pretty darn good. Okay, so I'm going to again begin reading. As the center of the nervous system, the brain is the most complex and powerful tissue of the human organs. It controls people's consciousness, processes external stimulation, information, and controls advanced activities such as thinking, emotion, and movement. Just a simple comment with respect to consciousness. Consciousness is a known concept, but there is a lot of conversation from it. So while the authors are citing something that says the brain controls consciousness, and that would seem to be the most common concept that people would work with, it's not necessarily something that we can be perfectly confident with, because it may at least be possible that it is a confluence of other things, or that consciousness is kind of an accident and maybe it lives in the brain, maybe it doesn't. The reason that we would believe that it lives in the brain is because when brain function is minimized, such as when somebody's in a coma, we see no signs of consciousness. We see a lack of consciousness, at least with the way that we use the term. So that's a lot of rambling about consciousness, but there's not a bad assumption, but there's an assumption there. Right? To read again, brain decoding is one of the hotspots in research of the neuroscience field and involves computational models that describe the correspondence between brain activity patterns and external stimuli and predict external stimulus information from the observed brain response activity. Thus, the main goal of neural decoding is to take a discriminative approach to understanding the measured activity that carries the information produced by different stimuli. And in this study, activity refers to the stimulation of human visual areas as manifested by the formation of functional magnetic resonance imaging. Okay, so to make it clear, what that is attempting to say is that they will have functional MRI images of the brain, which mean that it's not necessarily a still image. It can be a recording, right? So it can be more like a video, say a bunch of images in sequence. The fMRI of the brain records a proxy. It does not record neural activity directly. We have not figured out a way to do that. It records blood flow, cerebral blood flow, and it will do it at varying levels of resolution. So I think the term, I believe, and I may be wrong, the term is a voxel, right? So they'll take a small portion and try to get it as fine as they can, and they're tracing blood flow to a particular region. Now, that particular region then is interpreted as, actually, it's not that. That's not what's happening. That region is just recorded as activity blood flow activity here, so we have a strong reason to believe that neural activity happened here, especially when you see it in sequence. So it's not a bad proxy at all. It's just that it's a proxy. They're not measuring neural activity. They're measuring something that co-occurs with neural activity at a fairly fine resolution. So that is a good method. It's just not necessarily what most people think it is. Most people think that an fMRI is recording neural activity. It's recording a proxy in the form of blood flow. It's a good proxy. It's not perfect, and it depends on the particular resolution that they're recording it at. So essentially what they're going to have done is presented a known image to somebody, recorded the fMRI activity, the brain activity through the fMRI, to correlate those two things. So first they had to prove that with reliability, that when a particular image was shown to a subject or multiple subjects, that a particular general pattern of blood flow happened within the brain. Now, it wouldn't even matter where that blood flow happened. It would matter that it happened. Now, there's a degree to which if you were imaging the whole brain, it would be very confusing. So what they've definitely done is zeroed in on the assumed region of the visual cortex. Now, the visual cortex is pretty stable person to person, but there can be variation as with anything else. So at least if you narrow your image or your recording to the area where the visual cortex lives, then you record the activity there, then you're zeroing in. So you're making a choice that you're not going to record the whole brain and get all that complicated data. You're going to get a little simpler. You're going to zoom in a little bit to the visual cortex. I think that's a good decision. It's just not necessarily the decision that would allow you to fully understand the interactions that are happening in the brain, because it might be too complicated and too variable. But if you go to the visual cortex, you record the blood flow through the fMRI, and you know which image it is. Now you have something you can test an artificial intelligence against. So what you're going to do is you're going to train that artificial intelligence with the pre-existing fMRI data that it knows was associated with a particular image. So you have pre-training of the artificial intelligence. Subsequent to that, when you decouple the image from the fMRI, you just give the artificial intelligence or the graph convolutional network the fMRI, so there's no known image data. It will then be able to output a prediction of what the image is based just on the fMRI data. And because that is a very specific task that needs learning to have happened before, it's doing a really good job on that task. The fear would be that it would then be able to, over enough time, predict anything that was happening in your brain. Now, the problem with that is that, let's just say for the same output, or for the same input to the brain, so the same sensory input, you could have some very interesting variable activation throughout the brain for varying reasons, because it's going to depend on what the brain ends up needing to do with it. So you can have the visual cortex data and basically just say the relatively raw input to the visual cortex. But then what you need to do is look at or what you would want to do rather, is look at the rest of the brain and see what varying individuals do with it, right? So how do people actually interpret images? It's not in the visual cortex. The interpretation of the image is probably going to have to bounce around a little bit. But when you just examine the visual cortex and the raw sensory data, then yeah, sure, a computer can do a good job of predicting what the raw visual data was outside. So what the stimulus was outside of the brain, especially if you trained it over time. Now, the challenge is that each individual is a little bit different, and you have variations in vision and variations in how a particular individual would be wired. So you can do a really good job of this, especially if you make your data big enough. But what this is doing is just predicting based on previous knowledge what the raw sense data is. It's not predicting how the person would interpret it or how the individual brain would interpret it. It's not predicting what they would then do with it, because it's not looking at that. So with respect to pre-learning, then predicting raw sense data in the visual cortex, these systems are actually doing pretty good. And then just to reiterate, this is functional MRI looking at blood flow, not neurological activity. So it's looking at the blood flow pattern. Now, an interesting thing about blood flow pattern is that it's probably a little bit more stable than neural firing specifically, because neural firing is more complicated, where blood flow is less complicated. There are less blood vessels, far less blood vessels than there are nerves. So as a result of that physical reality, it might actually be more intelligent to attempt to use blood flow to understand what's going on, because you can track it better. So it's one layer less complex as far as what we could observe than neural firing. It's a good proxy for region. You're getting into a region, but it's not necessarily telling you what's really going on. So if you attempted to switch from blood flow observations to neural observations, this might not work at all, or it might be too complicated with technology we have available at the moment. Okay, so there's lots of interesting things here that we don't need to go through. I want to get down to one of the charts, and I think, or one of the figures, and it's actually, I'm just going to do this really quickly so you see what they did. The 11 ROIs, so this is figure 2, the 11 ROIs of the proposed algorithm, including V1D, V1V, V2D, V2V, V3D, blah, 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 blah. So you see a bunch of areas that they've chosen to focus in on. So you understand they made a choice in the visual cortex of where to observe, and they're showing you that with the figure. Now, if an individual's blood flow is just a little bit different, now we know that cerebral blood flow is different in different individuals. The areas have to be supplied, but the way that they're supplied is a little bit different. So that's a layer of complexity. So the common description in anatomy textbooks of cerebrovascular flow is the circle of Willis. And apparently the circle of Willis is only present fully in about 25% of people, which means 75% of people, it's not that they don't have the blood flow, it's just constructed different than the circle of Willis as a representation, right? So they made choices. They didn't look at the other areas, they looked at the areas they've outlined, if that, hopefully that makes sense. So they didn't look at everything, they looked at the areas they chose to. All right, I'm going to try to get to, I think it's figure 4. It might be, oh, table 4, sorry. Yeah. No, I'm wrong. So there's lots of math here, and the math is important, and I'm not sophisticated enough, unfortunately, to understand if it was good. These are the tables. Okay. So table 4, it's got different systems. So their system is all the way at the bottom, and what you see is the categories on the top, right? So there's a lot of categories of predetermined images that they trained the AIs with. So they had the fMRI data from a bunch of people that saw an ostrich, the same picture of an ostrich, the same picture of a hummingbird, the same picture of a battle plane, the same picture of a backpack, blah, blah, blah. And then what they were able to do is take new fMRI data that wasn't coupled, so they were able to decouple it in all of these systems. And then the artificial intelligence or the graph convolutional network would output what it predicted that it was. And what you can see is that the comparison of experimental, the performance, average performance, these are pretty high numbers for something that's just predicting raw sense data, or it's making a prediction from something it previously knew off of raw sense data, which is actually how our sensory system works. We have raw sense data, we start to make interpretations, we start to then add words to it. Once we add those words to it, or the phonemes, rather, the sounds that carry meaning that we then interpret, what ends up happening is every time we see an example of something, maybe it's the same, maybe it's different, but we start to zero in on the features that are the same within a category. So you can see, say, an ostrich and an emu and tell them apart, although they're oddly similar, there are enough differences that you can tell them apart, right? A hummingbird versus another type of bird. Well, your categories are going to be size, how fast its wings move, how does it fly compared to other birds. A battle plane, there's a lot of battle planes, so that's an interesting category. A backpack, well, backpacks come in different sizes, shapes, colors. They have more straps, less straps. But you start to understand that if it's got 2 straps, and it's a kind of sack-like, and it's got a zipper, and it goes over somebody's back, right? You've seen them there, then now it's a backpack. Now, the computers, the graph convolutional network isn't doing that. It's just interpreting the raw sense data. So it's not going to likely be as good at discriminating between backpacks, but it'll be really good at predicting the backpack it knew about before, if that makes sense. Where are we? All right, table 5. Again, really high accuracy rates in most of these, some a little bit lower, right? Like a water balloon seems to be not as good for anybody. Light bulb seems to be bad compared to other things. So it's actually harder for the computer to the AI or the graph convolution network to predict a light bulb. If you look at this, table 6, comparison, the F scores, blah, blah, blah. Yeah, so the average accuracy, the one in the paper that they're using is performing at 98.6%, 6-7%, whereas the other ones are low 80s to high 90s, right? So that's really what I want to share. Now, to show you that you have to know what it's actually doing to understand it, and understand that it's not necessarily this big scary thing where AIs are going to be able to read your thoughts, because that's not even what's happening. What's actually happening is it's taking pre-learned data and pre-coupled data of a stable image and multiple subjects and their fMRI in very specific areas. It's then able to be decoupled, and when you feed it just the fMRI data, what do you predict that this person saw? And then it's able to choose from what it knows. So the computing power required to do more than that is quite high. The fMRI data is also quite expensive. So to put somebody in a functional magnetic resonance imaging machine and then read their thoughts or predict what they saw from a pre-learned and stable stimuli, it's impressive, but it's not reading thoughts. It's not like your cell phone is going to be able to read your neurological conductance in your brain. At the moment, it's not going to be able to read the blood flow in your brain. You would need a pretty invasive thing to be able to do either one of those, neural activity or blood flow in the brain. So to read it outside of a functional magnetic resonance imaging machine is essentially not possible right now. It's not impossible, it's essentially not possible. And there's brain-computer interfaces and things of that nature. I don't believe, from what I understand, they're functioning at the level one would hope. They're functioning, as far as we know, in primates. There are issues there, but that is what it is, and I'm not necessarily going to talk about that. But for one to take the jump from a research article like that, because that's essentially what the article that I saw, the news article that I saw that said that AIs are going to be able to read your thoughts, that's the research it was pointing to. It was pointing to the fMRI and visual decoding. So the assumptions there are that at the level of granularity that they're following blood flow, that's an appropriate proxy for neural firing. It's a really good proxy, I fully admit that, but the assumption is that it is the proxy that's required. And at the granularity, or maybe higher granularity, they'll say that maybe they need to get more, say, fine-grained with how they're scanning that. The assumption is that blood flow is stable enough between individuals and that they chose the correct areas to observe. Now, just because you choose particular areas and you get a good result on a stable image, like on the same image between people, so everybody looks at the same image, their output is read in those areas, not other areas, but in those areas, and then you're able to predict off of it, right? It's impressive, but it's not reading thoughts. It probably, if you showed it a different hummingbird, or if you showed a person a hummingbird from a different angle, the fMRI might not be able to predict it right now, or the graph convolutional network might not be able to predict it right now because it hasn't been trained on that data. So it's possible that it could be, but that doesn't mean it's going to read your thoughts, because you're not going to be in an fMRI all the time. Until a new technology comes around that can stably and reliably read blood flow or neural firing in the brain, we're not even close to reading thoughts, like not even remotely close. So the assumption that the whomsoever wrote the article that I initially saw made is that that's reading thoughts. They didn't understand the methods, and they didn't understand the choices that the researchers had to make. And I would say the researchers made good choices, and the researchers didn't claim that they were reading thoughts. They to take you through that as maybe a more current concept to help you understand what will happen in osteopathic or hands-on practice with respect to diagnostics and claims from those diagnostics is essentially that what we want to understand is from the environment of observation outside the patient, what can we interpret about the inside of the patient? And the answer is relatively little, right? So let's just say you want to consider the vagus nerve and the fact that it runs through the cervical column, and then you are going to make the prediction that the complaint that the person has about digestion is because of the vagus nerve, right? And you're going to say that the finding that you had in the cervical column, the cervical restriction, was putting some form of pressure on the vagus nerve, and therefore that's why they have a digestive problem, because the complaint that they have is within the range of the foregut, the midgut, and essentially the first 2/3 of the hindgut, more or less, right? So the first 2/3 of the transverse colon up to there, and everything above that within all organ fields is getting parasympathetic tone from the vagus nerve in almost everybody, with variation. Now, you're saying the patient has a complaint of the digestive dysfunction, you find a cervical dysfunction, and you say it's the vagus nerve, right? Now, for it to be the vagus nerve, you've made a bunch of assumptions, right? You haven't depressed or lowered parasympathetic function, which means that the heart rate and respiration should be higher, and then all digestive functions should be maybe working in a disrupted way. So if you want proxies that are measurable from the outside of the patient for vagal functions, heart rate and respiration are good because they're observable from the outside of the patient. You can palpate pulse points and measure that. You can just watch the breath and measure that. You can give it a time frame, and then however many times it happens within that time frame, that's a frequency, right? So cycles per minute, beats per minute, relatively common frequency measurements for every point along the way to be correct. And I will say that there's major problems with the manner in which that's done. So how come the cervical dysfunction disrupted the vagus nerve and not the upper limb or the brachial plexus, right? So there's a lot of ifs that have to be satisfied. If you want to talk about vagal function, measure heart rate and respiration consistently with the patient, find a cervical dysfunction, and then prove that heart rate and respiration change in a meaningful way for a period of time, whatever period of time that is. If you've got a bunch of visits with a patient, they're willing to do it, well, measure their heart rate every time they come in, measure their respiration every time they come in, treat only their neck and nothing else. I mean, absolutely nothing else. And then have them come back a bunch of times and then see what happens to their heart rate and respiration. And for it to be accurate in a free living situation, you would want to monitor their exercise as well, because if they're getting fitter, then their heart rate and respiration will change. So there's a lot of variables confounding here for somebody to make a claim that a cervical dysfunction is definitely changing heart rate, respiration, and digestive functions because of the vagus nerve. So the amount of ifs, the amount of assumptions that are made from the external environment of observation with osteopathic practice is exceptionally high, right? To work from the outside of the patient and use patient report and palpation to couple anything about the liver is less than accurate. It's less than ideal. What I really want to say, if I'm pre-speaking, is that it's insane. The problem is that most practitioners, because of the manner in which they're taught, they don't know the amount of assumptions that they are making, that they think they're correct, because they can't think with other details because they don't have them to be accessed. Just like the graph convolutional network wouldn't necessarily be able to predict if somebody saw their spouse, right? Or a picture of their spouse, or if they saw their child, a giraffe, versus a picture of a giraffe. So if you saw a free living giraffe or a free roaming giraffe, and the AI had been trained on fMRI data for seeing a picture of a giraffe, it might not actually pick up giraffe in the free roaming giraffe. Like it might not pick it up because there's a layer of difference. It's more complicated, right? So because it doesn't have the previous details, it can't do it. Because osteopathic practitioners don't have the details, that the assumptions that they make about coupling patient report, palpation, and then making a claim on that is not an accurate thing to do based on the environment of observation and the assumptions that must be made with the reporting or with the information that they have. The fact that they don't know that's nuts means that they're not necessarily nuts, they're underinformed. So hopefully these conversations help you understand how being more informed with more details can be helpful. And you can see how the feature is the same in osteopathic diagnostics as well as the article or the news article that I first saw, as well as the research article that I went through with you, all have assumptions. But if you can't track where the assumptions are, you can't track where the problems might live, and you can't understand how much you could trust it. So if you stay on the wave tops and on the superficial level, you trust it a lot. When you start to dig down a little bit deeper, your confidence can shift a little bit. So it can increase or it can decrease. With the respect to the research article, I'm in a decent place with the choices that they made and the claims that they made. I'm in a bad position with trusting the claims that the news article made, and I'm in a bad position with the claims many osteopathic practitioners make about patient report coupled with palpation, then making an interpretation and saying it's this structure, that structure, this nerve, this vessel. It's low level behavior with respect to diagnostics, and I think it could be a lot better. Now, the simple suggestion that I've made before with respect to osteopathic diagnostics is if you use a motion test, which is the only test you have, and you make a motion claim, you're accurate. The moment you go at any level internal to the patient, you're losing levels of accuracy because you're losing accuracy of observation. So be really careful with the claims that you make and the claims that you'll accept from other colleagues. Just be cautious. So hopefully that was useful for you, and hopefully you see how both of these examples that I'm giving are examples of the exact same underlying structure or the exact same underlying problem. It's the issue with assumptions, and especially assumptions based on environment of observation. So thanks for listening, and we'll talk again soon.